Hello, IB. We're looking at 12E and 12F, so both of these sections in this one video. Operations with plane vectors. So vectors that are in two-dimensional space are vectors that are drawn on a plane. So they have two directions, our x direction and our y direction. So we have vector A, which is given to you as x direction is A1. So if you notice this first vector, here's vector A. And the x direction is represented by A1, so we're going A1 units to the right. And then our y direction is represented by A2, so we're going A2 units up. And so we have our beginning and our end representing vector A. Vector B is added on to vector A, and we are going from the arrow end of vector A, B1 units to the right, B2 units up, and that gives us vector B, which goes in this direction from start to finish. And then you have this resultant vector in red, which is A plus B. All right, so this red vector here is A plus B, so we started here, ended here, and that's your A plus B vector. If we actually gave vector A and B some values, then we could just add them together and get our resultant vector by using vector addition. So for this one, if we have vector A plus vector B, what we're doing is really just adding our components together. So -3 and 2 is representing vector A, and if we add vector B, represented as 1 and 4, then we get our resultant vector, which would be our A components, or A1 plus B1, which is our X components, added together. So -3 plus 1 is -2. And then our Y components, this would have been our A1 and our A2 and B2 added together. So 2 plus 4 would be 6. Okay, so if we actually gave these values in the diagram up here, if we gave these components some values, so our X component and our Y component, if we gave them some values, then we could have something like this. And again, remember, addition is commutative, so I could also add vector A plus vector B in the opposite order. So B first, 1 and 4, added to A, -3 and 2, and I would get my resultant vector of -2 and 6 again. So it does not matter what order you add your vectors in. So similar to addition, when you have negative vectors, you're just adding the opposite, just like we do when we add negative numbers together. So if you look at vector A here, we have an X component of 2 units right, a Y component of 3 units up. If we just turn A around and put it in the opposite direction, so now A is traveling kind of southwest instead of northeast, we are moving -2 units in the X direction and -3 units in the Y direction. So this first vector here would be represented as 2, 3. And the second vector here would be represented as -2 and -3. So if you think about A to -A, we're really just multiplying by -1. So if we have -1 multiplied by 2, 3, so -1 is our scalar, we wind up with -2 and -3. All right, so just think about that vector as a completely opposite vector, and when we add vectors together, we are really add negative vector, we're really adding the opposite. So here, if you take a look at this example, we have vector A, just going from here to here, from start to finish. If we added vector B on, we'd be adding in a positive direction, but since we're subtracting B, we're taking that same magnitude, but taking in the opposite direction. So we have A plus -B, or A minus B, as our resultant vector shows. So when we subtract vectors, we're really doing the same thing. So P minus Q would equal P minus Q, all right, which is really saying -4 minus -1. So we're really just taking the -4 and the 2, and we're adding the opposite vector, so +1, +5. All right, so we will result with -3 and 7. If we go back to the beginning, -4 minus -1 would be -3. 2 minus -5 would be +7. So there's our resultant vector when we subtract our vectors. All right, so applying a few other operations. If we have scalar multiplications, remember if A is a certain length and we multiply it by 2, we double the length for A, and there we get 2A. So similar, for any k value that is a scalar, we just multiply that k value by whatever your components are. So you'd multiply k by your x component and k by your y component. So just think for a moment, if your k is -1, that is similar to what was happening here when we were subtracting vectors. So you just get the opposite vector or a negative vector. If k is 0, then you would wind up getting 0 and 0. So you would get the 0 vector. So let's see what happens algebraically. If we have -3 times vector p, -3 is our scalar. Our vector is 1, 5. So we wind up with a resultant vector of -3 and -15. All right, so that -3 multiplies by 1 and -3 multiplies by 5. Now we have two ways of looking at a vector or notating using notation for our vectors. We've got our unit vector form and we have our component form. So the component form is the familiar form that we've been using a lot, where you have your x component and your y component. Unit vector form just represents your x component in terms of so many units in the direction of I, which is directly to the east, so 1, 0. So remember your I is 1, 0. Your j is the vertical direction, so that would be 0, 1. All right, and then when we get into 3D space, we will also have a z component that will add on. But for right now, our unit vector form and our component form, we're being asked to find the magnitude of vector p minus 2q. So whatever that resultant vector looks like, and we were going to find the magnitude of it. So let's first do it in unit vector form. So let's find what is p minus 2q. In unit vector form, we would have vector p, which is 3i minus 5j, minus 2 times vector q, which is -I minus 2j. So if I wind up simplifying this, I have 3i minus 5j, which is my first vector p. I'm going to multiply my -2 as a scalar. So I'll wind up with positive 2i and positive 4j. And if I add my components together, so 3i and 2i make 5i, so I'm treating them just like pronumerals, and -5j plus 4j is -j. So what happens now is when I take the magnitude of p minus 2q, remember 5i minus j is a vector, and to find the magnitude of it, it's using Pythagoras basically, because we have 5 units in the x direction, -1 unit in the y direction. So let's figure out how long, so 5 units to the right, 1 unit down, and we want to know how far this vector actually travels. So how long is this vector? What's the magnitude of the vector? So I'm going to use Pythagoras by taking my x component, so 5 squared, plus my y component, which is the -1 squared, and I wind up with the square root of 26. So this is units, whatever that length is. Okay, so square root of 26, and whatever the units we're representing as the length of that vector, which is the magnitude of the vector. I can do the same thing in component form. So for component form, we'll take p minus 2q again, but this time we'll write our p as 3 -5 minus 2 times our q, which is -1 -2. And then again, I can take 3 and -5. I can multiply my scalar. So I'll have 2 and what is that, 4. And then if I put those two together, I wind up with 5 and -1. So again, I can find my magnitude. I'm using the exact same values for my x component and my y component. So we take the square root of 5 squared plus -1 squared. And I still wind up with the square root of 26. So you guys just read the directions very carefully if they want you to use unit vector form versus if they'd like you to use component form. If the question's given to you in unit vector form, stay with unit vector form, all right? Component form, if the question's given to you in component form, obviously, then write it in component form as well. All right, guys, these were our 4 ideas for, let's see, this was section E, so we are now going to move on to section F, 12F. All right, guys, so 12F introduces a vector between 2 points. So that means you are now given a coordinate plane, and we have to think of point A as a position at A1, A2, and point B at the position B1, B2. If I want to represent the position vector of A, I'm going to go from our origin 0, 0 to A, and I can think of this as vector from O to A. So we will call that, vector OA. And then you've got also vector OB, which is a position vector if I go straight from the origin out to B. So now this is my position vector of B to represent the position of B. However, if I want to now connect position A to B, I am actually moving from A to B. So I have to think of going, if I start here, I would have to travel negative OA plus OB. So negative OA plus OB would actually be AO plus OB. All right, and then therefore that actually will give me AB. So what we need to think about doing is if I'm going to start at A and go to B, I'm actually going to be subtracting OB minus OA, all right, which is really what's happening here. So I'm taking OB and I'm subtracting OA. So if I have a position vector for these two, A and B, points A and B, then I can subtract OB minus OA, and I can wind up with vector AB, which is what I'd like to do in the end. So let's take a look at how this actually works. Again, in your book, you have a position vector of B relative to A, so in other words, traveling from A to B, and if we take OB and subtract OA, we'll wind up with AB. All right, so here is where you guys should see that in your textbook. Similar idea, just with different notation. All right, vector CD, we take vector D and we subtract vector C from it. You can also think of it as a translation. So how are we translating from point A to point B? So you can think of it almost like a translation vector. How are we moving from one to the other? All right. So just to put it into practice here, if I want to talk about a vector that represents the position of B relative to the origin O, all right, that means I'm going to take my point B and subtract the origin, which is 0, 0. So I will just wind up with 3, 4 as my vector OB. However, if I start at A and go to B, so I want a position vector of B from A, that means I want, so from A to B, I actually want vector AB. And as we discussed on the previous slide, that means we are going to take vector B, which is 3, 4. We are going to subtract our position vector of A, which would just be -1, 2. So I'm going to find how far did I move from A to get to B. So I'll subtract B minus A. So that means I have moved 4 units in the X direction and 2 units in the Y direction, and that is my vector AB. Similarly, if I went to A from B, that means I would want to go from B to A. Now, since I've already found AB, I know it's going to be just the opposite, so it should wind up being -4 to -2, but let's go ahead and use our points just for practice. So B to A means I'm going to subtract A, which is -1, 2, minus B, which is 3, 4. and -1 minus 3 is -4, 2 minus 4 is -2, and we just proved that yes, that actually does work. So we did wind up getting the opposite vector of AB, meaning -4, -2 is BA. All right, we're going to leave you guys with one question today, and that is, if AB is the diameter of a circle with center C, so here you're given the center C, AB is the diameter, and B is at position 3, 1, find vector BC. So if I'm going from B to C, how could I represent that vector? Just as we did on the last slide. And then if I know this vector from B to C, could I find the coordinates of point A? All right, so go ahead and work on that, and we'll start with that in class next time. Have a fantastic evening.